Let's start. Do you have any questions? Right. So we were discussing conditional distribution, which is 6.5, I think. Yeah. Okay. So in kind of some summary, basically you have formulas, right? Which are the probably what you most commonly have to do. So the formulas are following. So if you have two discrete random variables, then the probability x equals to, let's say, I condition y equals to j, right, is probability x equals to I, y equals to j over probability y equals to j, right? So here you should think of this as j being fixed. Okay, I can change. And so if you have xy continuous, then you have the conditional density, which is the joint over the marginal, right? So again, right here, y is fixed, x can change. So the reason, right? So I guess the first thing is to remember that the theme is conditional is joint over marginal. And then, so the second thing, right, besides, of course, just applying the formula, is to remember, right, that basically conditional distribution is a proper random variable or distribution, okay, in and of itself. Meaning that basically, yes, we call it a conditional distribution, but if you hide the word conditional, that's fine. It's still a distribution, right? So you could just talk about it like a distribution. For example, right, here, that's exactly the importance of I fixed, J fixed I can change, right? Because if you sum, right, over all values of I, you will get one, right? So it's a total probability. So this, right, basically makes it into a probability, right? notice that actually if you do the other way, if you sum over J, right? I mean, you can sum it, but who knows what comes out, right? It could be a number less than 1, bigger than 1, whatever. And this is exactly why, right, J fixed, I can change, is the theme, right? Same thing with the, this actually is a proper density, right, in itself, meaning that if you integrate the conditional density with respect to X, okay, in this case, over all value of X, whatever that is, you will get 1. All right. And so of course, this is non-negative. Okay. And so it is a distribution. It just arrived at, or it's just defined using conditioning. So for example, right, a very important concept which we'll encounter a little bit in chapter 7 is called conditional expectation and conditional variance. All right, these are very important concepts in advanced, a little bit more advanced probability. So if you look at, say, conditional expectation of X given Y, right? If they're both discrete, that will be the sum. So first of all, right, it's just like this. Sum of all values of X. Or if they're both continuous, then it's the integral over the conditional density. So you see, right? If you cover this, then it's just really about the regular expectation formula. But so that's exactly it, right? This should be looked at as a probability and as a density, period, right? And then variance, right? Ouch. Conditional variance will be conditional expectation of the squared minus the squared of conditional expectation. And we have shown how to define, right? So basically here is we X squared in here, and here it'll be this guy squared. Right? So that concept, or you can basically do anything you want, anything you can with conditional distribution as you can with regular distribution. Last but not least, right, let's try to mention again that when you have continuous, right, random variables, then probability of X being in some region, right, but condition on, let's say, Y equals to a value, must be calculated using conditional density. Okay, it cannot be done via definition because probability, right, of Y equals to little y right is they're both zeros. Okay, so this won't make sense for continuous distribution, but this expression still makes sense via conditional density. All right. well, I just say this is last but not least, but one more thing is conditional distribution can be defined generally, right? And will be defined for any xy random variables. What we mean by this is that you don't need discrete or continuous random variables. Like you don't require them to be both discrete, both continuous. They can be whatever. They can be mixed, right? Or one continuous, one discrete. Of course, there you don't have like a concrete formula like this, right? You have to use, I don't know, some more advanced calculus slash thinking slash whatever to arrive at the distribution. But the concept, right, works in general. It's not this is not a definition. This is more like a formula to explain how you can describe the distribution in these two particular cases. Okay. So we've done a few examples last time. Let's look at one last example today, which is 6.46, right? And just to point out one thing. So here you have the joint density as C x squared minus xy e to minus x minus x less than equal to y. All right. Find the conditional distribution of y given x. All right. So what do we see here? First of all, right, if you look at this, you see that there's a C here, right? What is this C? We've seen this C before, right? This is called the integrating constant, right? Which means that it's there, right, to ensure that the density or the probabilities add up to 1, right? Or integrate up to 1. Right. So I guess here it should be dy dx, right? C. Okay. Now, you may or may not have to find C depending on the work you do. Of course, if you want to find concretely, say probability x less than y, whatever, right? I mean, I guess here it's already given. But if you want to find some probability concretely, then you need to solve for C. On the other hand, right, here you want to find the conditional density, right, of y given x. And as it turns out, the conditional density, right, of y given x will be determined completely without knowing what C is. What's the reason? The reason is pretty simple, actually. The reason is because the division will cancel out the C on both top and bottom. Okay, so let's see. So here you have to find the marginal of x, right? So if you have to integrate out of y, right? And what do we get out of this? So you get C, right? The first term gives you 2x cubed, right? The second term, you have to integrate, right? But y squared is y cubed over 3 over an even interval. You pick up twice, right? From 0 to x. So you get 2/3. Right? Meaning 4/3. Right? And so the conditional density will be, well, you take, right? So let's just write it down just to be clear. So see, of course this cancel, but that's not the main point. The main point is C here, right? Get canceled. So you get something like 3/4 x squared minus y squared over x cubed, where the main player here is y, right? So y is between minus x and x. So again, you see right here, you should see that x here is a given value. So x is fixed, right? X is like, 2, 3, whatever, right? Who knows? And then y moves between those two ends, right? So here x is fixed. The row of x and y are not symmetric, right? X is fixed and y changes. But yeah, right, there's that theme there that I want to point out in this problem. I mean, the calculation is routine. But the theme is that when you do conditional distribution, then the undetermined coefficient, the undetermined integrating constant will wash out, right? And it will not show. And this fact actually is very important in, say, important sampling. It's not important sampling. Monte Carlo, Markov chain Monte Carlo, MCMC, Monte Carlo simulation, because when you look at those, when you do sampling, Monte Carlo simulation, a lot of times you come up with a distribution, but it's going to take a long time to figure out what the integrating constant is. And if your work is about finding the conditional distribution, then you don't really care. You don't need to spend time solving for that integrating constant. Okay. All right. Any question? All right. So let's move to the next topic. So 6.6 will skip is all the stats. Not that it's not important. Skip for now. But it's going to be a topic that's picked up in statistics for A1, for example. So let's take a look at 6.7. Transformations of random variables. So joint distribution of functions of random variables. All right, so first let me tell you the main question, and then we'll say the result. So the main point, right, remember actually we looked at this before. So basically you have a random vector, right? Let's say x1 up to xn, right? With some joint PDF, right? F of x1 up to xn. Now you will transform this into, let's say, function phi1, phi2, etc., up to phi n, right? This is x1. And you just call this, for example, y1. Okay. Then you want to find what's the joint PDF here. Let's call that, I don't know, G, right? A simple example, right? I mean, of course, we have seen, for example, I don't know, right? X is uniform 0, 1. Y is e to x, right? This is like the one-dimensional case, right? But you could have something like a two-dimensional case, which is probably the most common here. You have xy with some joint density. And then you can look at maybe, right, one of the popular distribution will be x plus y over 2. You know what? Let's say x plus y minus x minus 1. And let's say you call that u and v. Then what is the joint PDF of u and v? All right, like that. So that's the question, right, that we're answering in this section. And more or less here is a formula, right? Unlike other things that we do in this course where I try not to kind of just do a straight formula. Here, well, there's some reasonings which we'll explain, but it will be more or less a formula. So let's write down what the formula is and we'll explain. So the formula, right, is as followed, and it's just for two-dimensional case. But it generalizes. So you have the context, right, is that you have x1, x2, all right, with joint density fx1, x2 given. You have y1, y2, which is g1, x1, x2, g2, x1, x2, all right? So these are the map, right? Like x plus y, x minus y, x1 plus x2, x1 minus x2, etc. Then the joint density of y1, y2 will be the original density of x1, x2. Well, the formula says this, but we'll explain. And then times the Jacobian x1, x2 inverse. All right. However, let's just say right away that this must be expressed in terms of y1, y2. All right. And where the Jacobian, so this is the Jacobian inverse. Okay. So 1 over the Jacobian. And this is the determinant, right? This means the determinant. So the Jacobian, oh, sorry. I take it back. This here already means the determinant of the Jacobian. This means the absolute value. So here, the notation will be the Jacobian, the determinant of the Jacobian you have seen in Calc 3. So partial G1 over partial X1, partial G2 over partial X2, G1 over partial X2, G2 X1. All right. So again, it's a formula. So let's do one or two examples to show what this means, and then we'll talk about the reasons. Okay. But right off the bat, right, let's note right away that the way it's phrased like this, everything naturally will be in terms of x1, x2. But you need to transform it into y1 and y2 because that's the target, right? That's the variable we're interested in. I mean, to make it kind of a little bit more confusing or whatever, a lot of times this will kind of turn out to be constant, like a number, like 1/2. So what I tell you here may not apply in some problems, but in general, you have to pay attention. Because if you were to give the answer that involves x1, x2 here in your final answer is completely wrong, okay? Because this is just a density of y1, y2, so everything has to be in terms of y1, y2. And then again, right, there's an inverse here, there's an absolute value for you to pay attention to. But let's take a look. I guess, right, maybe the easiest one is let's even look at a one-dimensional question, right? So just to show you how the formula works for any dimension, really. I mean, right, you just basically generalize this to n dimension because there's nothing special on the number 2 here. It's just really whatever, and then the Jacobian can be extended to n dimension or one dimension, right? So let's take a look at one dimensional, right? So here, right, it say the formula reads the density of y will be the density of x times the Jacobian, right? Inverse. But let's take a look at what that is. So the density of x is 1, right? So 1 is 1, doesn't matter if it's a function of x or 1 is a function of y, so we don't need to transform it. So let's say it's 1. What about the Jacobian? Jacobian, right, is here, so the function, right, e to x. So the function, the Jacobian of x is partial e to x over partial x, which is e to x, which is already positive, right? Because e to x is positive. So we don't need to take absolute value. But it's 1 over that. So it's e to minus x, right? So but it has to be given in terms of y, right? It has to be given in terms of y. So therefore, it's going to be 1 over y. All right, where y goes from where to where? Y goes from 1 to e. Does that make sense? Well, let's take a look, right? How would we do this? You know, with our approach before. the approach before would work with the CDF, right? Probability y less than or equal to y is probability e to x less than or equal to y is probability x less than or equal to log y, right? And that's because x is a uniform 0 to 1, that's log y. Therefore, the density is 1 over y, right? And so you see, right? And I think I've noticed some of you have already used this formula on the midterm too. Who knows where you got it from, right? Maybe the textbook did that in the previous chapter. I don't know, right? Because I don't see a need for to use the formula. But the formula works in one-dimensional case, right? And it's a particular case of this. All right. But like I said, I don't know. It's a taste because if you do this right, well, you get the right answer. But I would prefer this approach for the one-dimensional case because I know exactly what I'm doing. But when it comes to higher dimension, then the CDF approach becomes messy. So you really have to rely on the formula, right? But let's show what the example is for two-dimensional, and then we'll explain the meaning of the formula. All right, but any question before we continue? All right, so let's say x1, x2 are independent. Exponentials. Let's say lambda 1, lambda 2. Okay. Which means the joint density is lambda 1 e to minus lambda 1 x1, lambda 2 e to minus lambda 2 x2, right? And we want right like that. We want to find the joint density, right? So let's start with the first question. Find the Jacobian of x1, x2 inverse, but of course, right, in terms of y1, y2. Professor, I think this might be quiz 2. Oh, appreciate it because we had a quiz 1 before, right? Thank you. Appreciate it. All right, so what's the answer? So here, right, this is the function g. This is the function g1, g2, right? So it's really what? 1, 1, 1, minus 1, right? So I guess I'm so used to Jacobian as a matrix, but the notation here means it's determinant, so it's minus 2. But after you take the absolute value, and then take the inverse, then it's going to be a half, right? So that's that. And so you see, that's what I was saying about a lot of times it's going to be a constant, so you don't have to worry about it. But right, don't let this fool you into forgetting, right, that you have to make the conversion. For example, here, right, you have to convert this into 1 over y, right? All right, so quiz 3, find the joint density of y1, y2 in this case. Right, so this is the joint density of x. What's the joint density of y? So notice, right, the formula says it's the same density, just multiply with J inverse, right? Determinant Jacobian inverse. So it's just this, but of course it cannot be this, right? It has to be in terms of y. So notice that technically speaking, right, I would prefer the formula to read like this. So by the way, right, the formula just copied down from the textbook, but in my opinion, it could be written like this for clarification. G1 inverse. Hold on. Yeah. And then here, right, it could be written as the Jacobian of y1, y2 inverse as well, determinant. So this is, again, take whatever formula you want, right? And there's some reason why this is a little bit not preferred because it sort of has more notation, blah, blah, blah. But what this means, right, is that you solve for x1 in terms of y1, y2. And you solve for x2 in terms of y1, y2. And this really is the other determinant, the other Jacobian, meaning that you solve for y1, y2, you have the G inverse function, and you take the Jacobian, right? Let me show you. But this really is the spirit. But anyway, right? So let's take a look. For example, here, right, if y1, y2 is this, then if you solve for x1, x2 in terms of y1, y2, you get right. So clearly, y x1 is y1 plus y2 over 2, and x2 is y1 minus y2 over 2, right? So this is what we mean by G1 inverse and G2 inverse, right? And so you will plug it in. So let's just finish the problem and I'll tell you one more thing, right? So you just plug this into the function. So the answer here would be the joint density of y1, y2 will be 1/2, right? Which is the Jacobian inverse, whatever. And then lambda 1, lambda 2, e to minus lambda 1, y1 plus y2 over 2, e to minus lambda 2, y1 minus y2 over 2, like that. And don't forget to write down the range of y1, y2. What range does it have? Y1 being the sum, right, will be between 0 and infinity, but y2 being the difference will be okay so far. Any question? You know what? Yeah, go ahead.
Back in the Jacobian, like quiz 2,
yeah.
How do we get positive 1/2? Are we taking the
because of absolute value?
Jacobian matrix?
Because of absolute value. In this transformation, you always take the absolute value of the determinant. That's actually one thing that you might have seen in Calc 3 that you forgot. It's always, so basically it's absolute value of determinant of Jacobian, something like that. So the reason is the textbook, right? This textbook put the determinant into the notation J. So this turns out to be the absolute value. That, yeah.
Okay, I carried the negative. Thank you.
Yeah. All right. So sorry, what I wrote down before is actually incorrect. I wrote this. Right. I wrote this, and this is actually incorrect. And that's actually a good mistake to notice. The reason is because even though it might seem like this, the restriction is more severe. The restriction is because you plug y1 plus y2 in here in place of the x1. And x1 by definition is a positive variable. So the range is that y1 plus y2 must be positive, and y1 minus y2 must be positive. This is the range of values. All right. Meaning that if you want, right, then minus y2 is less than y1, and hold on, sorry. Y2 is less than y1, but minus y2, y1 is greater than minus 1. Okay, whatever. Hold on, what do I want to say here? Yeah, so y1 is bigger than both, right? So yeah. So if you draw the picture, then here's y1 equals to y2, here's y1 equals to minus y2, right? Then y1 is bigger than both. That means that's the range. So you see, right, it's true that y1 is positive and y2 takes on both values. But if you write like this, you will, right, think of this whole region. But no, right, the restriction is more severe. It's only this part. Is that okay? So the range here has to be more carefully pay attention to. Any question? All right. So one last thing I want to show you is if you take this function, which are the inverse, right, of the map here, right? And you take the Jacobian of it. Let's see what happens, right? So Jacobian here would be differentiated with respect to y1, y2, right? So if you take the Jacobian of that, whoops, you will get 1/2, right? 1/2 minus 1/2 minus 1/2, right? Which, as you can see, is minus 1/2, which of course is the same as the answer you get above. Well, without the absolute value, right? If you take the absolute value, it's exactly 1/2. And so the answer will be the same whether you take the Jacobian inverse of the inverse map and take determinant, or you take the Jacobian of the forward map and then reciprocate it, right? And that's actually a result of linear algebra, right? Determinant of the inverse is 1 over determinant, as long as the determinant is non-zero. So whichever way you take is fine. And so that's why, right? So what I'm saying is like the result of the result of the transformation of the density. Actually, everything is about the inverse, right? Plug into the original form. But I think maybe just for presentation and to make things easier to look at, the textbook would present it in terms of the forward map. Okay, and then just say express in terms of 1, 1, 1, 2. So whichever way you want to take it. All right, any question? All right, so let's try. So let x1, x2 be independent standard normals. Right, that means the joint will be 1 over 2 pi e to the minus x1 square over 2 e to the minus x2 square over 2, right? Which really is 1 over 2 pi e to the minus x1 square plus x2 square over 2. They're both between minus infinity and infinity. Find let y be the same, right? x1 plus x2, x1 minus x2, find the joint density of y1, y2. All right. So what do we have? So we have 1/2 here, right? That's the same. And then the 1/2 pi, right? Now we need to do this in terms of y1, y2. Well, how do you do that? Well, y1, y2 is this, right? So here's a neat trick, I guess, right? That you see x1 plus x2 squared plus x1 minus x2 squared will be what? 2x1 squared plus 2x2 squared, right? Therefore, this is just y1 squared plus y2 squared over 2, or y1 squared over 4, y2 squared over 4. Right. Now, what is the relationship between y1 and y2? Well, unlike the above result, where we need this to happen, because x1, x2 are positive, here, x1, x2 are any number, right? Therefore, there's really no restriction on y1, y2. I mean, again, if you really want, you can say something like this. Sorry, this is lowercase y. Okay. So you can say something like minus infinity less than y1 plus y2 less than 30, minus infinity less than y1 minus y2 less than 30, which is probably a healthy habit to do. But if you investigate this, you see that it has no restriction, meaning that okay. Now, last but not least, let's look at this joint density. And what do we see? We see that it's actually split, right? Because it's a product of two functions that does not involve y1, y2. In other words, right, this is 1 over square root of 4 pi eta minus y1 square over 4 times 1 over square root of 4 pi eta minus y2 square over 2, over 4. So what have we concluded? We have concluded that, right, that if x1, x2 are independent standard normals, then x1 plus x2, x1 minus x2 will be independent, and each of them will be a normal 0-2 random variable. And it's the independent part here that's most interesting, because you see, right, they both have x1, x2 in them. But this is to show you that independence is a subtle thing, right? That the rule of thumb that, you know, somehow they have nothing in common works, but doesn't, you know, have to, right? So that's why we need rigorous result or rigorous tools to check here that both that they're independent. But of course, this result only applies to the standard normal, right? As you can see with the exponentials, they clearly are not independent. So any question? So, all right. So, right, I guess part of the message, right, is that this result, the transformation, right, will also allow you to conclude about the joint behavior of Y1, Y2, in particular when they're independent. But it's a nice thing to have in some cases, but don't expect that to happen all the time, right? Meaning that when you do the transformation, somehow things split, right? But that's why, I guess, if you want to think of like maybe a potential application of this result, it basically is about finding appropriate transformation so that your original density becomes independent, maybe. And one more remark is you can see that, right, the number one challenge in applying the transformation, besides the complexity of the formula, right? And I am completely aware, right, that this formula, as simple as it may sound, I don't know, uh, can be and will be applied incorrectly many times, right, for the students. I've seen it enough to know that. So the conversion from X into Y is the challenge. But of course, applying the formula correctly is also a challenge, right? So, but I would assume that you can apply the formula correctly. Then the remaining part will be this, right? To do the transformation, to find the conversion, right? For example, here, if you don't know this sort of like combination, then I think it may take you a while, right? It should not be that long. You just do y1 plus y2 over 2, y1 minus y2 over 2, and you square it, and you should get some sort of things like that. But right, if you know the combination, then it will be faster for you to work with the transformation. All right, any question? All right, so let's take a look at another one. Let x1, x2 be independent standard normal. Again, so like quiz 4. Let r squared be x squared plus y squared. Let theta be tangent inverse of, oh, sorry. Here we just want x and y. Y over x. And so you see, right, you know what this is about. This is about polar coordinates transformation. Right. So what this really talking about, at least in terms of the geometry of it, right, is that you have coordinates, right, rectangular coordinates, where you sample, right, the points according to a normal distribution across each coordinate. All right. As you'll see, it's equivalent, and actually it's this one. It's equivalent to sample the points along circles, where the angle will be sampled uniformly, and the radius will be sampled according to I believe, an exponential distribution. But we'll see, right? That's actually the outcome of this. So the question, of course, is to find the joint distribution of r squared and theta. You know what? Maybe let's break it down a little bit, right? Maybe let's try to ask you to find what? Find J inverse, right? J of xy inverse. In terms of r squared and theta. All right, so let's take a look, right? Here and probably here also, right, is where this notation sort of makes sense, or this approach, because if you try to do the inverse approach as I was mentioning before, right, meaning that you solve for, you know, the original variables in terms of the transform variables, then here, right, you have to solve for x and y in terms of r squared and theta. Again, it's not bad, right? It's r cosine theta, r sine theta, right? We know that because of the polar coordinates. So in fact, maybe it's not bad. Let's show you both, right? Let's see. So if you do the forward transformation, then you got what? Partial r over partial x, right? Which is 2x, and then 2y. Derivative of tangent inverse is what? Anyone remember? 1 over 1 plus x squared, right? So 1 over 1 plus y over x squared. But then if you differentiate to x, you need to do the chain rule, right? That's minus y over x squared. And then respect to y, right, will be the same. But then multiply with respect to y will be 1 over x, right? And so let's see. If you take the determinant of this, right, you will get what? I guess here the x cancel. You got minus y squared over x squared, right? You got x squared over x squared plus y squared minus, right? You got minus y squared over x squared here, right? Which if you multiply across here, so that's plus y squared. Well, hold on. So actually, sorry. So there's a 2, right? But it seems like the only thing that's left is a 2. Yeah, right. And of course, then the Jacobian inverse is a half. Right? But if you were to do the inverse map, let's see if that works, right? If you were to do the inverse map, then x is r cosine theta, right? And y is r sine theta. So if you were to do the inverse map, you will get what? Partial x over partial r is cosine theta. Partial x over partial theta is minus, right, r sine theta. Y over r is sine theta, right? And then partial r cosine theta, right? So if you do this, you got r cosine squared theta plus r sine squared theta is r. So that's a bit weird, right? Because here, when you do the, oh, you know what? Sorry. It's really not the forward map because here's r square. Here's r square as a variable, right? Here, we look at x as the inverse function of r. So it's not quite the one-to-one correspondence. So that's probably, I mean, yeah, right. So the inverse map doesn't quite correspond because if you do the inverse map, then you're really looking at the r rather than r square map, okay? Yeah, but anyway, so that's your Jacobian, right? And so how do you find the joint density of r squared and theta? Well, the original, right, density will be 1 over 2 pi e to the minus x squared plus y squared over 2, right? So therefore, in terms of the substitution in, you will get 1/2 1 over 2 pi e to the minus r squared over 2. That's it. What's the range of values? 0 less than r less than infinity, right? Because r squared. What about theta? Theta is tangent inverse, right, of y over x. Now, y and x takes value between minus infinity and infinity. So a tangent inverse of a number between minus infinity and infinity, all you can say is theta is between minus pi over 2 to pi over 2. Right? So, hold on. Is it minus pi over 2 pi over 2 or between 0 to 2 pi? Just give me a moment here. So the right answer between 0 and 2 pi, but I'll give me a moment to think about it. But so there's no restriction on theta, the range of theta, rather than its inverse function. Well, we'll explain that later, right? But the point is, right, let's take a look at this. This is a function of r squared, right? But where's theta here? For example, where's theta? Well, the answer, right, is actually this is why theta range is not between minus pi over 2 to pi over 2, but it's 0 to 2 pi. The reason is actually this is theta right here. The density of theta is right here, right? So if you take a look, this will be 1/2 E, sorry. Yeah, 1/2 e to minus r squared over 2, and then times 1/2 pi. Which, right, looks like what? Sorry, it's not fxy, fr squared theta, right? And then forget this. That's just plugging in, right? So what I meant was you have fxy, which is 1/2 pi e to minus x squared plus y squared over 2. So if you plug in for r squared and theta, you get this, right? So the point, right, is that if you look at this function in terms of r squared and theta, you see that r squared, right, r squared should be looked at as one single number, will be, it's like e to minus, some number u over 2. So that's why it's an exponential 1/2 random variable. And theta, right, because the density is 1/2 pi, so r squared, right, and theta will be 1/2 pi. So that's why it's a uniform from 0 to 2 pi distribution. And more importantly, these two, right, is a product. So basically r squared is independent of theta. So to recap, right, if you want to sample, right, a pair of normals, independent normals on the xy coordinates, then what you can also do is to sample a radius as exponential 1/2. I mean, radius square, right? Take the square root of that, and then take a point uniformly around the circle. Then, right, that pair will be the same as the independent normals that you sample with the rectangular coordinates. Any question? All right. So this, right, is not just a mundane result in terms of transformation of polar coordinates, transformation of joint density, right? What it really means is also about how to simulate normals. So if you want to simulate independent normals, which is the topic of Monte Carlo simulation, it's not that easy, okay, to simulate in normal random variables mathematically. But it's relatively easy to simulate like uniform and exponential. So what you can do is you simulate, right, a pair. Like I said, right, you simulate r squared, which is exponential 1/2, and then you simulate theta, which is uniform 0 to 2 pi. Then you can define x1, which is r cosine theta, define x2 as r sine theta. When you do this, you will have x1, x2 as independent standard normals. And that actually is a very well-known algorithm to simulate normals, okay, in the computer. All right, any question? All right, so let's just do more problems to make sure you get the techniques in. So quiz 6. Suppose xy have joint density one over x squared times y squared, y bigger equal to 1. Find the joint density of, let u be x times y, v be x over y. Find the joint density of u. Okay. So again, right, the formula is what? The formula is fuv of uv, right, is fxy of xy Jacobian, right, of xy, determine inverse absolute value. Everything in terms of u and v, right? So let's find the Jacobian first. So the Jacobian will be partial u, partial x, partial u over partial x, right? Which is y, x, and then partial v over partial x is 1 over y minus x over y squared, right? Which will be minus x over y minus x over y is minus 2x over y, right? So which, right, as you notice, has to be in terms of v, so minus 2v. And so the absolute value of Jacobian inverse, right, will be what? Well, it's just 1 over that. But notice, what does absolute value do? Well, of course, it turns minus 2 into 2, but what about the v? Notice that, right? Because u and v here are going to equal, so x and y are going to equal to 1. When you divide it, v is automatically positive. So the absolute value will just be 2v. Right? And so the density of u and v clearly will be what? Because xy right there is 1 of x squared y squared. So it's going to be 1 over u squared times 1 over 2v. Okay. What's the range of values? The range of values, right, don't be mistaken. Because, I mean, or don't be too hasty, right? Here, because x bigger than 1, y bigger than 1, what we'll need is what? So if you look at u and v, right? Well, let's see here. I want to say this. If you multiply u and v and you take the square root, right, you get x, right? And if you divide u over v, take the square root, you get y, right? And so x bigger than 1, y bigger than 1 will translate to u times v going equal to 1, u over v going equal to 1. Again, right, this may or may not have any restriction, but any real restriction, but I believe it does. So let's take a look, right? So this is u, this is v, right? U times v equals to 1 for the positive is just a hyperbola, right? And u equals to v, right? It's just a line. So this is u equals to 1 over v. So u greater than equal to 1 over v means to the right of this. And u greater than equal to v is to the right of the line. Right, so together is this region. So yes, right, I think it has a very real effect. So in other words, are they independent? Are u and v independent here? My suspicion is no. I don't think they are independent. Right? I mean, the follow-up question in the textbook will ask you to find the marginals of u and v, right? So the next one will be find. You know what? Maybe let's just throw that into, right? And we'll see that they're not really independent. Right? Any questions so far? Right. So quiz 7. Find the marginals. In the previous problem. All right, so what's the answer here? Well, if you want to find the density of U, right, then you need to integrate this out with respect to V, right? But if you look at V, right, so I guess you can factor out 1 over U squared, right? And then you have the V here. But V would go from where to where? V would go from here to here, right? Which is 1 over U to U. Right? Which means you got 1 over U squared, let's say 1 over 2U squared, log V, right? E to U, which is 1 over 2U squared, log U minus log of 1 over U, so 2 log U. So it's log U over U squared, where U is greater than. Right? What about the density of V? The density of V will be integrate out the U part, right? So 1 over 2V, integrate out the U part. Where U goes from where to where? Well, so you see here, right? Actually, the density of V will be tricky, right? It depends on where V is. So this point, right, is 1, 1, right? If V is less than 1, then it's a different value. But if V is greater than 1, it's another value. So the density of V, right, will be for V less than 1, then it will be integrate from 1 over U, right? Sorry, 1 over V to infinity. But if it's bigger than 1, then that's 1 over is V to infinity. Because this is a line U equals to. All right. And then whatever that is, let's, skip that part. But any question about this? So that's really it about the transformation, right? There are two things we can do right now for the last, I don't know, 25 minutes. We can either do more problems, along this line just to show you more problems with the same technique, or we can move on to chapter 7, which is about, expectation and things like that. Any preference for either way? The reason I ask is because this tends to be the, I don't know, trickier topic for whatever reason, right? It's really just technical stuff, but maybe the more you see it, the better, but it's up to you. Maybe you have seen enough. I don't know. Any preference for either way?
Could we do a problem where we do it both ways, like first by the map and then like both ways of the formula?
Which other way are we referring to?
Like the one where we first use
CDF?
everything in terms of x, y, and then we do everything in terms of function and then switch x, y.
Hold on, I'm still not following. So what are you referring to? This formula I'm referring that?
Yeah.
Okay, so first of all, right, this formula is always in the air. It's not really different from what we've been doing. The reason is as follows, okay? The reason is because, first of all, when you plug in for y1, y2, you already solve for x1, x2 in terms of y1, y2, right? Or you already solve for x and y in terms of theta and r squared. So it's always that to begin with. I was more or less just point out the nature of the expression, but it has always been that way. Meaning, right? You see here, you change into u and then v, right? Meaning that it's always like that. So the only thing, right, is that, like I said, the textbook, like write this as x1 and x2, which is like the original PDF, which I find a bit misleading because the point is you have to solve for x1 in terms of y1, y2, and that's just the notation right there. The only potential difference is this guy, right? Where, right, you can either do the forward Jacobian, meaning that you can just take the forward map, right, like this, and differentiate with respect to x1, x2, and then take the reciprocal. Or you can do the inverse map and then just differentiate. And that, as I tried to explain, is the same number. And a lot of the time, the forward map is easier to differentiate because the inverse map, when you have to solve for it, it might be harder to take the derivative. So all in all, actually, the formula of the textbook is, let's say, superior in terms of calculation. But the conceptual content is this one, because it's sort of like going back from y to x rather than moving forward from x to y. So when I write this formula down, I don't really mean it to be used 100%, but I want to kind of make the conceptual connection of what you actually are doing versus what the formula the textbook wrote down. But we've been doing that all the way through all these examples.
That makes much more sense. Thank you.
Sure. All right. So any other question, or you want to see more examples? All right. So if there's no preference, last chance, then let's move on to chapter 7, okay? Because I feel like it'll just be a repetition of the same technique, so you can just do it on your own with your homework. So let's move on to chapter 7, which is properties of expectation. Where, remember, right? 7.7 MGF, right, is a kind of expectation, right? It's expectation of e to tx, which we have discussed, right? But so let's move on to, let's see, 7.2, because 7.1 is just general introduction. You know what? Maybe let me just talk about 7.1 a little bit from my point of view. So basically, right, that in a lot of problems, all we're interested in let's say is either expectation of a random variable or variance of a random variable. And notice that actually this also covers probability of x bigger than equal to x. So maybe the first thing to mention is that expectation covers probability as a sub area, even though the technique may or may not apply to it. Here's the reason. So probability is an expectation. All right. The reason is, right, when you learn probability, let's say in this course, you learn probability first and then you learn expectation. So you might think that these two are two separate topics. In fact, right, in more advanced point of view, or right now even, you can expectation is the general concept and probability is just a sub part of it. Here's a reason, right? Recall the Bernoulli. If x is a Bernoulli P, right, meaning that probability of x equals to 1 is equal to P, and probability x equal to 0 is 1 minus P. Then expectation of x, right, is P. P times 1 plus 1 minus P times 0, which is exactly probability x equals to 1. And there you go. That's really it. Probability is an expectation. Now, you may object and you say, well, that's just probably x equals to 1, but we have so many other kinds of probability. Well, the answer is, right, x equals to 1 here is just a placeholder for something, right? Because we never say what x is. If x equals to 1, if an event E happens, right? And x equal to 0, if E complement happens or E does not happen, then you see that probability of x equals to 1 is exactly probability of E. Meaning, right, that you can say that x is the indicator function for the event E. Therefore, when you take expectation of random variable, you really are looking at a probability event. So the techniques, if it applies, when we talk about expectation, can also extend to probabilities. Okay. So that's why, like, the whole one whole chapter 7, right, is devoted to expectation, because in a rather non-intuitive way, if you study expectation, you actually cover many things, including, right, the whole distribution of the random variables, like the MGF, right, moment general function. All right. Now, so that's the first thing. The second thing I want to say, right, is that expectation has a very nice property, which goes to 7.2 actually. Expectation, right, has, let's say, has several nice properties. The first thing is that expectation of the sum is the sum of the expectation, regardless of how the xi's behave. Of the joint distribution. Right? When it comes to variance, it won't be the same. Variance sum is not the sum of the variance. It's only true when they're independent. So this will open the door for many techniques. Well, just maybe one technique called the indicator function technique. This is 7.2, right? Or 7.2, 7.3, let's say. And then the second one, which is, again, a little bit more advanced, but if you take conditional expectation and then you take expectation again, you will get the original expectation. This is a very well-known law of expectation called, right? Some people call it double expectation, whatever. This right here allows you to compute expectation by conditioning, which is a very powerful technique that, goes into different areas, right? Statistics, finance, whatnot, right? So these two together are the reason why we care to study. Let's say we want the whole chapter is devoted to expectation. Variance, right, as you can see, is like a offshoot, right, of expectation, because expectation, the square must describe expectation. But right, to start with, that's that. So this is 7.5, 7.6. Okay. And so that's that. And then variance, right? Let's just say that variance itself is also very important because, in statistics, you care for, let's say, expectation and variance. We want to also see the equivalence or the analog of these two for variance. Okay. Because you want to apply the same rule, let's say, for variance. But with variance, I don't think the textbook, it may be on top of conditional variance. But the first thing definitely we'll need to look at, which is variance of the sum, is the sum of the variance plus the covariance. So that's the first thing, right? With variance, you have covariance terms attached. Not sure if we'll get to conditional variance in this course, and there's no need to. That's probably for more advanced courses. But if you also have a analog of conditional variance like this. Okay. So this will be topic of 7.4. This can be left for later courses, right? So there you go. Basically, it's these properties that we want to highlight and discuss. And also this one, expectation as a probability, right? That we want to kind of highlight in the chapter. Okay. So let's see here. In the last 10 minutes or so, let's look at 7.2, expectation of a sum. And so here, right, I think it's best to look at an example. And the example is something that we talked about at the beginning of the class and haven't returned to since. Is the hat problem, right? It says that there are n persons, right? Throw the hat together, right? And then pick out at random, right? And the question that we discussed at the beginning of the course is the probability that no person gets the right hat, right? Which is an application of the inclusion-exclusion formula. But right now, the question we want to discuss is expectation of the number, let X be the number of persons with the right hat. And you want to find this number. Okay. And as you will see, a theme in calculating expectation for this kind of chapter is the following, is that you don't use the formula for expectation. I mean, again, right, when to use, when not to use, who knows? That's exactly the challenge of more advanced problems. The reason is the following, right? If you think of X as a random variable, takes values in what? 0, 1, up to n, right? Because no person can get the right hat, one person up to n persons. Then you may think that expectation of X is, right, the sum of K, probably X equals to K, right? K runs from 0 to n. Which is correct, it's a formula, it's correct. But of course, right, no one will give you any credit for writing this down because you're just writing down a definition. The whole point is to calculate out what this is, right? And the first thing is you should realize that probably X equals to K is, let's say, something to deal with. Why? Because it's going to be the probability that exactly, let's say, K people, right, getting the right hat. Which, if you remember, right, is sort of like a mix of the inclusion-exclusion formula, right, with this question, right? Because if K person gets the right hat, that means n minus K person, exactly n minus K person must not get the right hat, right? So, and even if you write that down, then that sum is a scary sum to deal with. It's much scarier than, let's say, the sum of the binomial. Okay, so all in all, this is really not an advisable approach. Okay, so what else can we do, you ask? What we can do is, right, to break down a random variable when it has to do with something like a total, right? Because this is a total number of persons with the right hat, into individual terms as a sum. Because, right, expectation of the sum is a sum of expectation, regardless of how the individual terms behave together. And the individual terms can be much easier to deal with. What does that mean? For example, in this context, you let xi to be 1 if the ith person gets the right hat. And 0 otherwise. And you can see that x here, which is the number of persons with the right hat, is a sum of xi. And so here, xi signifies the indicator function of the ith person getting the right hat, right, of the event. So that's an indicator function. And this is the use of the indicator function to count up to the total number, right, of something. So notice one thing, right, that the xi are not independent. Why? Simple, right? Because if the ith person getting the wrong hat, then of course it will influence someone else, so on and so forth, blah, blah, blah. So they're not independent. But on the other hand, the expectation of xi is simple. Because xi is a Bernoulli function, right? Bernoulli random variable. So expectation of xi is probably xi equals to 1, which is probably the ith person getting the right hat, which is one over n. Therefore, expectation of x will be the sum of expectation of xi, but these are all 1 over n, right? So the answer is 1. And so you see, right, an amazing thing is this scary sum, whatever that was that I was describing, it sums up to 1, regardless of what n is. And so there lies, let's say, the beauty of that technique, that, you know, when you try to take advantage of a expectation or somewhat random variables, you can get very simple result by analyzing the individual component and not worrying about how the component interact. All right, any question? All right, so if not, I think it's a good place to stop here, and we'll pick it up on Friday.
Thank you.
Sure.